learning is a summary of Verilog basics and how do we write Verilog code, sequential logic, and what are the sequential constructs for writing the combinational design in Verilog, and a little bit of finite state machines. Okay, so first, the basics of writing Verilog code is assuming that whatever you are writing for, considering it as a module will be the main building block in Verilog. Okay, so similar to C, C++, or Java, here we represent using a module. So we start with a module to represent anything, the any functionality. Let it be a half header, a logical gate. Okay, so we'll say module and gate, module half header, module full header. So module will be the main building block. Next, so if you first need to declare the name of the module, okay, and followed by the connections, the input and outputs of this module. As you can see here, this is your basic building block. It's a Verilog module because it is written in a Verilog code. Okay, and this ABC are the inputs and Y is the output. Okay, so first name of the module, types of its connections, names of its connections. That's it. Okay, so this is the module example ABCY. You can have any gate or the elements that we have in our combination circuits. Okay, you can say module SOC, module, you can name anything, module CPU, module RAM, module ROM. Okay, so every component or everything that you are digitally building the block, okay, using Verilog code, we just represent it, and how many input ports you have for it, and what are the outputs. Okay, and once you declare inputs and outputs, after that we provide the behavior or a circuit description or the functionality of this particular module. Okay, and after that end module. Let's see with some examples later. Okay, so first we'll start in defining these ports with a bus. Let's say I have a 32-bit bus in a a is a port. Okay, and it is a for 32-bit bus. Okay, so similarly you have output of uh, b 8 down 15 down to 8. So this is the allocated for b1, and 7 down to 0, again it is allocated to b2. So these are split for a 16-bit output. These are split into two output ports. So this is the range of the data bus of this particular port. Okay, so A0 to A31, total 32 bits of EA port, okay, is a input. So if you want to define the data bus of this particular port, okay, you will be defining it in the square brackets with a everything starts with 0 here, so 31 down to 0, so it's a 32-bit. So 15 down to 8, okay, here we split into 8 bits, and again output 7 down to 0 is again 8 bits. Next, input clock. So clock doesn't have bus. So in general, we never define buses to the clocks because clocks doesn't come in data buses. So clock behavior is different. So A might be a data bus, B might be a data bus, okay, B2 might be a data bus, but clock is not a data bus. Okay, it's not a data, it's a clock. Is this clear here?
Sir, once more.
So why can't we go with the
Why can't we go to? Sorry.
uh, here we declare that range starts with in input A
Mhm.
31 to 0, right?
Yes.
31 down to 0.
Hmm.
So why can't we go with the 0 to 31?
So this is a
Why you are only representing 31 to 0?
uh, so the upper value to the down value is a syntax that we have in defining bus. So it's not a we can also represent like instead of 31 down to 0 we can just mention 32 directly, or we can mention 0 to 31. So it's a behavior and syntax of the compilers to define bus. So there are certain rules and guidelines that tool accepts. So you are telling the tool that my data bus starts with 0 from LHS to the RHS, to the left to the right. Okay, this is the way you write the uh, code. So this is a one of the rules and guidelines that we follow in writing the code. Okay, so you can try
Okay, sir.
with the 0 down to 31. Okay, uh, tool will throw an error. You can understand it will throw certain error stating that the bus range should start from the high range end to the range start. Okay, so certain compilers, there are some um, there are some GitHub inbuilt compilers. They have a different range, different syntax. Let's say they start from 0 colon 31. It works for them. So it's up to how the compiler is and how the tool accepts. And this is Verilog syntax. This is basic Verilog syntax, how we represent buses, ports. Okay. So uh, that is the reason we are also following it. Okay. So any other questions other than the bus range?
Sir, could you please repeat?
Your voice is breaking. Your voice is breaking. Should I repeat it again uh,
Yeah,
from the beginning? Okay.
yeah, yes.
Okay. So this is a simple Verilog code. Okay. As you can see here, we are writing. We have taken example. We did not also take any gate here. Okay. Going forward, we'll see a little bit of examples of some combinational and sequential circuits. How we write the code. Okay. So the module example can be any functionality of logical gate or combination circuit or a sequential circuit, followed by in the brackets. Okay, it's a normal brackets with the number of input and output ports you want to have for this uh, your desired module. Okay, so let's say you have
Okay.
taken an AND gate. A, B are the inputs and pi is the output. So you will have A, B, Y for an AND gate.
Right.
So input
Okay.
A, input B, and output Y. Okay. So this is an
Okay.
example where you mention the inputs and outputs within these brackets. Okay.
Okay.
And a colon. So this is a syntax. Okay. So we
Okay.
have this syntax of we need to follow certain guidelines to represent the Verilog code. We cannot bypass this because majority of the compilers. So end of the day, uh, even in a C programming or a C++ or a Java, you give it to some compiler, right? Assembler or a compiler, and it compiles and it tells you if there are any syntax errors, or if there are no syntax errors, then it computes this module and gives you the required output. Correct. So similarly, Verilog has a syntax that we need to follow. So this is the way you define it. Okay. So we have to define inputs, input A colon, input B colon, input C colon, output Y colon, in this fashion only. This is a very introduction to defining a simple module. Okay. Now there is one more way of defining that we will see later. We can also write here itself input A, input B, input C, and output Y. So there are different ways of writing Verilog code. Okay, so that you will learn part of this course. Okay, so
Okay.
instead of writing here separately, you can write all of this here itself. You don't need to write here. So there are ways you can represent, you can write. So once you practice this, right, we'll get to understand in how many ways we can write it. Okay, and
Okay.
here we will describe the functionality. Let's say there is an AND gate. We are writing it for an AND gate. So y is equal to a and b. A b. A dot b means it's a and b. So tool will convert that functionality into a proper gate level after you synthesize this module. You give this code to the synthesis tool. Tool will first check the syntax, then it will synthesize it to a proper gate. Because this is just a code, right? You're writing a code for a gate, and once the tool synthesizes it, it will convert into a proper gate. Then you can see the schematic like a proper schematic of gate with the inputs and output in the schematic viewer. If you can write test bench for the same module, okay, you can mention that whatever stimuli you want to give in the test bench and what is the expected output you want, you can mention in the test bench. So you will get that, and you can see it in the waveform. So there is a practice. You can do a practice for this Verilog coding using. There is a tool EDA Playground, I guess. Okay, so I'll try to show you how it is done. There you can practice Verilog coding. It is helpful for everybody. I think every student from the college use this extensively because it's a free. It's a free tool, and for students, I think for colleges, if they're tied up with that, there is a professional or paid version of that EDA Playground, I guess. Anybody knows from coming from the recent passwords from the college? Anybody know this playground? EDA?
No, sir.
No. I think Lalita, you have practiced it, right? You know.
Yeah, yes, sir.
So what is the full name of it? EDA Playground, is it?
EDA playground, yes, yes.
Okay.
EDA playground.
Right. Right. Thank you. Yeah. So verification engineers use it extensively as part of their training because it's a free tool and open source tool available in the Google. You can directly go to the website and practice there. Okay, we will also do that. It is very helpful for you guys. You don't need to install some Xilinx or any other model sim. You can directly use this compiler, which will also provide you the waveforms also. Okay. Right. Next thing. So in the previous session, in the previous image that you have seen, we haven't defined any data bus, the bit length of the port. Right. Here we are defining it. Input 31 down 0 is a that a port is a that is having a 32 bit length. So the data bus, the data that you can give in the a using a, okay, a port is up to a input is a 32 bit. So 101010, likewise you can give up to 32 bit data you can give as the input. Okay, so that bus information you have to give in a square brackets from a higher end range to the lower end. Okay. So that is how we represent here. Is this clear?
So why do we use bus data bus here?
Bus is something that, let's say, uh, let me draw it here. Okay. So, do you know what is a what is your laptop processor? Is it a 32-bit, 64, 86?
64.
64. Okay. By default, 64 supports 86 as well. But let's say now your primary data inputs. So every SoC, every chip, okay, you will have the data length. Okay. So we'll have general purpose input output pins. Okay. Let's say these are your data pins, data input pins. Okay. Sorry, I would say ports. Okay. Ports are different and pins are different. Okay. Okay. So this you can take an example from 8051 microcontroller, right? You remember 8051 microcontroller? Okay. So the 40-bit pin that we have for this 8051 microcontroller. So we have data pins, okay, and other peripheral pins, okay, crystal oscillators, data address enables, and bidirectional and unidirectional pins. So here the data input, let's say we have A, B, and C. So A, whatever the ALU, your arithmetic logical operation unit can process, it can process up to, let's say, 64-bit of data input. Okay. So your bit length of this A pin should have 63 down 0, this much of bit length. Okay. So you can give 1011 or whatever the 64-bit input data input. So this is your bus. This is bus range. Okay. So for that particular module inside, there is a this is some full adder or half adder. Okay. So your full adder should support 64-bit input to process this data, because you are portraying it as a your processor can support 64-bit of data. So you can give 64-bit input and expect 64-bit output. I mean, it be depending on the functionality. Okay. So the data bus, input data bus, you provide this bus range based on how much bit length it can process the data. Okay. So let's say you have 4x1 marks. Okay. So when you have 4x1 marks, you have A0, A1, A2, A3. Okay. So this is a single bit data. Okay. So this A0 still you can make it a data bus of 32-bit or a 64-bit, but you should have that register, that means registers feeding into A0 to store that bit of data. So when you're saying that 64-bit 0, that means you are creating that means registers. Okay. That much of register bank you are creating. Okay. So A can store up to 64-bit data input. This is your bus range. Is it clear? Guys, clearer, not clear? Still confused?
Clear.
So did not understand why we use bus still?
Yeah, sir. Is this bus work as inputs in this Verilog code, right?
Bus works as a
Sir, I
input.
think,
Okay.
sir,
Tell me.
I think the bus is capable of transferring of signals, right? Transferring
Yeah.
of data.
I mean, it is storing the data. Later we will be using it for functionality.
Hmm.
The data will be, if it is input of some module, you are giving in 32 bit of data, and the module is performing the functionality as intended, and it is giving the respective output. Yeah.
Okay.
So if you say it is an encoder or decoder, similarly you will have 64-bit encoder. You will have a 64-bit decoder also. How much data you are getting as input. Again, you are going to encode it, and again you are going to decode it. Okay, so there you can talk it in the form of transferring the data. Okay, so bus can be used in terms of storing that much of bit length of data. Okay, that means this primary input can be fed with this much of data. If you don't give any bus, okay, you need to serially provide one after the other. Every cycle you need to give new data. Instead, if you give a bus, you can at a time give 32 bit of data to this particular input port. Okay, so going forward, you will understand once we move to the more complex circuits, you'll understand the usage of this. Okay. Here, uh, we have two way of representing. So this is called instantiation. Okay. So this is a structural Verilog coding. Okay. Structural Verilog, or sometimes we also call it as a behavioral also. Okay. So in real time, we see this a lot. Okay. So we call in real time we call this as a behavioral. So let's say this is a top module. Okay. Top module is this one. This is a top module. Okay. One moment. Let me plug in the charger. Okay. So this is your top module. Within the top module, you have two uh, small registers. Okay. Registers or gates or anything. Okay. I think this looks like a gate, not a register. Okay. So this is uh, one gate, and this is one more gate, I first and I two. Okay. Now module top, you have in the boundary of module top, you have A, select C and as inputs and Y as output. A select C and Y input, A select C output Y. Okay. Now there is a connection from I first to the I two, from here to here. You have to represent, for that you need to create wire. Okay, wire N1. Okay, so this is wire. This is a wire, right? Connecting from source to destination. Y is your source and A is destination. Okay. Now, your this is a small is a original module of this particular gate. This can be instantiated multiple times in the name of I first, I2, I3, I4, I5. As many times you can instantiate. That is called instantiation. Okay. So this is the original module. Let's say let's not confuse too much on instantiation. Okay, there is a module AND gate. Okay, A, B, and C. I'm directly taking it. So input A, input B, output C. Functionality C is equal to A, B, end module. Okay. Okay, this is clear here. This is my original module of AND gate. What is the module name? AND. Okay. Now I want to use this module AND in another module top. Okay. Let's say A, B, C, D, or E. Okay. And input A, I can say input A, B, C, output D and E. Okay. Now I want to have if I'm taking a block diagram of this top. Okay, I have AND gate here followed by another AND gate here. A, D, C. Okay, this is D. I have taken one extra, it's okay. Okay, this is my wire N1. Okay, now I am going to define a name for this. This is a original name is AND, right? And okay, and I'm going to name it as and 2 by 1. Okay, and I'm going to have the connections there. A input, B, okay, and this output. Let's say this is your D, okay, and let's say this is your E, and this is your F. Okay, now D is connected to a net N1. Okay, this is ending here. This module ended here. Again one more AND gate and 2 by 1. Okay, I'll make it as a 2 and 2 by 1. Okay, and the inputs are here for this particular gate again. Okay, N1, C, and here C is equal to F. Okay, N module. Okay, here mentioning the wire also, wire N1. Okay. So if you see here, this is my original module. Original module definition is here. This becomes my library. Okay. I will read in the libraries of this AND gate, OR gate, all the gates, and I will use this libraries to be instantiated. These are the original module from the library. I will be using the username. This is original name and this is instantiated name. This is called instantiation. I'm using this AND gate. It's a two by two input, one output AND gate, right? So I have written like this. Okay. Instantiation should not be same. Okay. It should differ. You instantiated this original name with one name. The second time, if you are using the same AND gate, again, you should have a different name. Okay. So the original AND gate pins will be the same names, A, B, C. If AND gate here is ABC, here also will be having ABC only. Okay. Within the circuit of top, what are the connections that you will have? That wires or names internally will be coming here. Okay. So this is the example for this. Okay. A select and N1. Generally, we make it this in a proper format. This is not the actual format. Okay. Even if we give this to the tool will take it, but this is not how you write. You write properly. Okay. So A, B, within A, again you will write A, B you will write brackets SEL, and Y you will write N1. Okay. This is your first instantiation. Again, the same original modulo small. Okay. This is your original modulo small. Okay. This you are writing it here in a different name, instantiated in a different name. Okay. Now, here you are writing A for A, N1, B, C. The C is going as input to B, and Y. Okay. In this example, you are understanding instantiation of one module in another module. You are calling this and using it. This is how you write SOC, because in your real-time designs, okay, you will have in an SOC, you might end up with one module to up to hundred, thousands, okay, 10,000s of modules. Okay, and again you will have multiple blocks within, as you know, CPU, RAM, ROM, okay, network module, all these modules connected internally. So this again in this you will write multiple internal submodules. Okay, so for that, this is the way you write it. You start with top, you start writing like this. Okay. First hand, this is generally, if this is a gate, this is called, this module is a standard cell. You call this as a standard cell. So what all comes into standard cells is logical gates, flip-flops, latches. Okay, let me take a new one. Logical gates, sequential circuits, anything that you already have a module, original module, you can define. Okay, special IPs or modules. Okay, so all these can be called again in writing in a instantiated in another module. Okay, this is clear. Did you understand what is instantiation? What is the original module here? How this code is written from the schematic that you see?
So what is a pin order, sir? What about that?
Pin order here. You can write, no problem. Any pin order will tool accepts. As long as the pin name is not changing, tool will accept.
So can we write A, B, and Y in that order?
So here, if you see, B, Y, A is a zigzag order they have written, right? You can write A, B, Y, or you can start with Y, B, A. Any order is okay.
Okay.
But a proper RTL code, when you start writing and synthesizing, tool sometimes arranges them as per the order once you synthesize it. Okay. Even if the RTL engineer is writing in a hurry, okay, he is practiced to write proper order. So this is just an example. In general, you will see a proper order, starting with inputs to the outputs, because it is useful for the next person to whoever sees this RTL code for them to understand. Okay, it will be in order in real time. Okay,
Yes, sir.
right. Can I move forward? This is understood by everyone. This is important, guys. This is important because though you will not be writing an RTL code, okay, you will work with the design netlists or RTLs coming into the DFT team from RTL team. You have to sometimes open the code and see if something fishy, or you want to trace some module, you want to trace some pin. Okay, let's say from A to this A, you want to trace it in the RTL instead of schematic. That is also a skill. We will learn it. I'll show you when the lab starts. Okay. So for that, you should understand the Verilog construct, how RTL construct is there and how netlist construct is there. Most of the time, RTLs will not trace, only will trace in the netlist and in the schematic. Okay. Tracing in the RTL is very difficult in real time. Okay. Because there will be multiple calling functionalities, and sometimes RTL is written in a system Verilog format. Okay. So we don't worry about RTL. We more worry about netlist, which will look similar like this, similar to this. Okay. Next. So this is a bitwise operators. Somewhere close to your system Verilog structure. Okay. So I mean, this is an RTL code. You can write as you wish. So the assign statements, you see here, the input. This is how I told, right? You can define the type of port here itself within these brackets. You don't need to write separately. So input 3 down to 0 for both A and B. Okay. Output 3 down to 0 for Y1, Y2, Y3, Y4, Y5. Okay. So this is a how much? How much is this? What is the bit length of A, B?
4.
Yeah. Okay. So 5 different 2 input logic gates acting on 4-bit buses. Okay. So now as in y is equal to, we are trying to do all operations of AND or XOR NAND NOR. So this is a symbolic representation of each gate behavior. Okay, while writing the code. So when you write these, okay, and give to the synthesis tool, because RTL has to be synthesized to gate level to start working for the physical design team, okay, or for the DFT also if he is using a netlist flow. Okay. So if you give it in this way, tool will convert this into the symbols to the XOR behavior. So tool will find a suitable XOR gate from the libraries. Okay. From the previous image, how you have found this, okay, and instantiated here, right? So once it's synthesized, it will get converted like this. Once this code is synthesized, then you will have a proper gate representation of these gates. You will not have symbols. Okay. So ASAN is one way to represent. Next, conditional assignment. Okay. So conditional assignment, you will come across only in SystemVerilog. We see these constructs in real time. Most of the time, you will not have this because certain tools like test and tools won't accept question marks. Okay. So Verilog construct should be very syntax and supportive for all the tools, all the EDA vendors. Okay. So certain tools doesn't accept. Only Synopsys tools will accept this. Okay. So question mark is also called a ternary operator because it operates on 3 inputs. Okay. Now here we are having mux. Mux is like mux2 means it's a 2 input 1 output mux. Okay. So it has D0, D1 select line and output as Y, and inputs are 3 down to 0. It's a 4-bit. Y again it is a 4-bit output. Now as in Y is equal to S. S is question mark because you can, it's a selective line, right? You have two options. So based on the input, when you write the test bench for this, you will write it as S is equal to 0. What should be the expected input of data input? D0 S value you will give and you will get expected output. Okay. So while writing RTL, you can make it as a question mark. This is a conditional assignment. Okay. So if
Sir,
S
how select line works?
select line works based on you select either data path 0 or data path 1. So here when you say when Y is equal to S based on the select line, you either choose D1 or D0. So if S, then Y is equal to D1, else Y is equal to D0. So this is the behavior of this particular code. Okay, this is one way of writing, guys. This is not how you actually write mux. This will not be the way you write mux. Okay, in real time. This is how you understand the writing way of writing. Okay, this is a way of writing a conditional assignment. In real time, you will not have mux like this. Okay. So your question is related to, I mean, did you, whatever I answered to you, is it okay for you, or you're asking in a different way how the mux behaves?
In mux, sir, in multiplexer, how select line works?
Okay. So this is D0, this is D1. Okay, and this is a select line. Okay, this is okay, D0, D1, SY. Okay. Now your question is how this select line works, is it?
Yes, sir.
Now select line is, you remember yesterday in yesterday's session we have seen the internal structure of a mux, right? With the AND gates and OR gate. You remember with inverter. let me see that I have already shared. Yeah. Do you see this? Okay. The logic diagram, and this is the truth table. Okay. So your select input is internally the mux will be like this with the two AND gates and an OR gate, and the inverter is either you select when S is equal to 0, S is equal to 0. Okay. Here it has to be enabled. So it is an AND gate, right? When you give 0 here and it becomes 1 here, right? So A0 value will pass on to output when the other input of the AND gate is high, right? Only when 1 and 1 comes in, then this value pass out. Okay. So when you give 1, then A1 is directly selected. Okay. So when you give 0, A0 is selected. When you give 1, A1 is selected. So this means your data input, you have two data inputs for a 2x1 multiplexer. When your select line is 0, your A0 is selected and exactly transferred to the output. Whatever input you have in A0 will be transferred out to the output. When your select line is 1, A1 will be exactly transferred to the output. At a time, only one value can be transferred to the output based on this select line. That is the benefit of this mux. Is it clear?
Yes, sir.
Okay. So give it some time. Okay. If you are completely new, just I have uploaded this document. You can go through this again, go through and understand, try to digest this, the truth table and logic diagram, try to give the values and see what output you will get based on this equation of mux. Okay. Okay. Right. So is this understood to everyone? Can I move forward? What is conditional assignment? How this question mark behaves? How do you understand it? I am not getting any response, guys. Did not understood this question mark. Why? How it behaves?
Yes, sir. Can you explain it once again, sir? That question mark.
Okay. So select line is a user choice, right? So a select line is a user choice. Which data has to be passed on to the output, correct? So the mux has this selectivity, which is a question mark, because which one you want to select? You don't finalize it here, right? Okay, you don't finalize it here. You finalize it in the test bench. When you have a conditional statement, that output depends on this conditional statement, whether S is 0 or 1, then you can make it as a question mark. So it's the same behavior of how you have a question, right? So you don't know what could be this, then you will have the question mark for that, right? So similarly, S is a selective line. So selective lines always have a question mark. Okay, and any conditional statement, if condition and if else conditions also will have this. Okay, but when you are using assign and conditional assignment statement like this is assign y is equal to s question mark. This is a conditional assignment statement. We are trying to understand different ways of writing RTL codes here. Okay, this is one way of writing. Okay, so when you write like when you have a situation of mux, you don't know which input you want to decide now itself while writing RTL code, then you make it as a question mark. You decide on usage. Based on the usage, it will change. You want to select S to be 0 or 1, it will change later when you synthesize or you when you use it in another module. Okay, understood?
Yeah, sir. So select line selects only one input, sir.
At a
If
time.
there is
Yes,
an n number of inputs, it selects only one input. And it delivers that
one
one
input,
input only or all the inputs.
only one. If it says
Okay.
0, then mean D0. It says 1, then D1. Only one input at a time
Then what
will be.
then what about
Yes.
another input if we mentioned?
So we don't want both inputs to drive at a time, right? So the mux
Okay,
is
sir.
a, so we are using mux. Mux behavior itself is that we have invented mux in our digital circuits for a reason. The reason is you want to allow, we have two data buses driving to the output, but at a time we want to allow only one, because your compiler or a digital processor cannot process two inputs at a time. That is called as a race condition. Okay, two inputs cannot be driven to one port. Okay, so let me show here. This is your mux. Mux output is going as a data input. Let's say data input, okay, of a flop. Okay, so does this flop accept two inputs at a time? Can it accept two inputs at a time? Can this flop process two inputs? It is, you're giving 0 here and 1 here. It cannot accept, right? It cannot process. So when you don't have this mux and two data inputs are connected, okay, directly to this D path of this particular flop, okay, this is called race condition. Okay, so this is functionally wrong. We will not have any such conditions in real time. This race condition is long back when RTL engineers are not efficient. They used to write like this. Okay, so we used to have tri-state bus or different uh, ways out how to get rid of this. If somebody has written it and later we can't change it, then we add one more logic to logic or delays to the paths. Okay, so the best solution is adding a mux. So you select only one path at a time. So one is processed one time and the another one is processed when you want to change it. So how you write? You write your condition as that uh, for some time s is 0, for some time s is 1. So it depends on how you want to use it. Okay, so the usage of mux itself is a condition where you want to allow only one input at a time. Okay, that is the behavior of a mux. Okay, clear?
Yes, sir.
Right. So the behavior of mux is something you want only one data to be transferred to the output at a time. Next. So how to express numbers? How do we express numbers? Okay. So this is n b xx as you see here. Okay. This is a syntax and this is a format that you follow in representing the numbers. Okay. So we have binary, hexadecimal, decimal, octal kind of numbers, right? So you just mention the base as b and the number of bits to be 8. Okay. This will show you how many bits will be used to store the value. Okay. So here how many bits you have? How many bits you have?
8 bits. 8 bits.
Okay. So the number of bits is 8. Okay. So base is base. You don't need to mention it as a hexadecimal, decimal, octal. Tool will understand automatically. Just mention it as a base. Okay. So you just give the number. Okay. So it's a 1. You started with 1. So the value expressed in base, apart from numbers, it can also have x and z values. Let's say this, instead of 1, you can have x. You can have x and z, or you can have all x's. That means uh, there is no data. There is no data when you say x. When you have z, it's called high impedance. When you say x, it's a x propagation. There is no data. When you say G, it's high impedance. It is also net data. X and Z are not values. Okay, not a real values. That means it is invalid or a invalid data. That is not a data. But you can represent X and Z in the representation of these numbers. Okay, this is a tool way of understanding it. So if you want to give a number to the tool, you have to give in this format. Okay, see the Verilog number representation, how you do. Okay, it's a 4-bit, you can represent like this. 8-bit, still you can represent like this, or you can represent like this. Okay, how you want to store, it all depends on the usage. So when you write again Verilog in a decimal, hexadecimal, octal, hexadecimal, hexadecimal. Okay, you can write in this way, tool will take it. But the way of storing the value will be like this. Okay, for this, the stored number is 1001. For this, the stored number is 0001001. Okay, you don't need to represent 4 zeros here. Tool will automatically take. That means if you have data, when you say 8 number of bits I have, but you mentioned only 4 bits of data, that means the remaining bits are 0. Tool automatically replaces them as a 0. This is how it is stored. And again, when you have like this, it will properly store it. In either of the cases, if you see, the stored number is the same. Here it is only 4-bit, that's why you have given 4 bits, you have taken 4 bits. Here, again, see, you have this value and this value, total 8 bits you have defined it here clearly. Tool will take as xx0x, 1zz1 as per whatever you have given. This is your 8-bit data. In this, the valid data is, how much valid data you have? 1, 1 and 0. The remaining all x's and z's are invalid. You don't have data there. Okay. Here, you did not mention the number of bits, you just mentioned D01. Okay. The stored data is, tool will not understand how to take it. Okay. Tool will not understand. When you give Verilog here in a 4-bit D5 decimal, you are telling decimal. Okay. It will take it as this 4-bit of D5 means if you do convert D5, this is the value. Then you convert 12 HFA3. This is your 12-bit data. You get 8-bit of 0, 1, 2. Okay. Tool will consider an octa in a octal representation of like this. Okay. 1, 2. Okay. Again, this is 4-bit of H7. This is the representation. Is all zeros. 12 bits of hexadecimal zeros. Okay. This is the way how the tool will understand when you give in a this while writing Verilog code. If you give this representation, tool will understand and store the number based on like this. Okay. So moving on to the tool acceptance of operations, the precedence of operation in Verilog. Okay. Not in order to mention not while writing a functionality in RTL code. Okay. If you want a NOT gate, you can just mention like this. Okay. Tool will consider this as a NOT gate. This is a symbol of NOT gate. For multiplication, it's a star. Okay. Division, it's a slash. Okay. MOD using percentages. For percentage, you call it as a MOD. Plus addition, minus subtraction, less than are symbols, shift left, shift right. Okay. Assign. Sometimes in a you will understand this. Okay. And this is if you have 3 arithmetic shift, and this is if you have only 1, that means it is a less than or equal to, greater than or equal to. It's a comparison comparator. Writing a code for comparator, you will use this. When you want to mention that it is equal, then you have to mention 2 double equals. And if it is not equal, 1 not. This is also symbol of not, but it is always used in this context. Okay. People generally misconcept with this not and this not. Tool will ask actually. Okay. Tool is a little bit clever in the way if it doesn't understand the syntax properly, tool will throw an error. Syntax error. So this is AND gate, NAND, and with the not, that is becomes a NAND gate. XOR, this is a upper curve. XNOR, not with a curve. Okay. Or this is a straight line you have in the keyboard. You can see above the slash. Okay. Or and NOR. This is a not symbol with a NOR. Or. This is a ternary operator. Ternary operators are nothing but the question mark. We have seen this already. Okay. So this is all order. Remember, guys, this is order. There is also an order. Let's say if you mentioned XNOR, okay, tool first considers if there is a not operation. If not, then it will go to the next. So not is the highest. This is called precedence of operations. The tool's understanding. Not is the highest precedence, followed by star, slash, okay, plus, minus. Okay, this is the order. Okay, I can move to next, right? This you will, based on some practice of Verilog coding, you will understand this, or going through some RTL codes, you will be able to get this. Okay. Give it some time and practice, you will get this. Those who are new to this, okay. I think those who are from BTech, recent passed outs, if they have VLS subject, I think they will have this. understanding. Okay, moving on. How? Any questions, guys? Okay. No questions. So sequential logic in Verilog. How do we write sequential logic in Verilog? Did we take too much of time? It's too late already. No, right? We started 9:30. I mean, in my time, for you at 8:30. Started at 7. Okay, we'll finish up this a little bit. Okay. So how do we define blocks that have memories? Because we are now going to write a Verilog code, we are going to see Verilog codes with a sequential logic. Sequential logic is something when you have what? What is a sequential logic? What we will have in sequential logics? Team, what will we have in sequential logic compared to what is the difference from combinational sequential? Yes, please.
Clock,
Latches, flip flop.
memory.
Memories, yeah. Clocks will come when you have memories, yeah. So sequential element, that means sequence can happen when either through finite state machines or you need a clock or reset for that. That is only possible when you have flip-flops and latches. Okay. So sequential logic is something which has flip-flops, latches, or finite state machines. Okay. Now, sequential logic is triggered by a clock, events of clock, or there is a other option that is reset. A flip-flop can be reset toggle with the two triggering points. One is clock, the other one is reset. Okay. Reset is not mentioned here, but I'm telling you guys. So latches are sensitive to level of the signal. Latches are level sensitive. Flip-flops are edge sensitive. Flip-flops will only transition based on the clock. Latches can just go with a level sensitive. They don't need a clock. Okay. Next, combinational constructs are not sufficient. We need new constructions. For sequential logic, we cannot just depend on combination constructs. We use sequential constructs. What are the sequential constructs? Always and initial. So we will be using always and initial for a sequential constructs because there is a dependency, right? So flip-flops and latches are dependent on clock and reset. So how do we write a program, write an RTL code to include flip-flops, these memories? Okay. Always statement, the syntax is like this. Always at the rate, okay, open braces, sensitivity list where you mention what is that, always what is the condition, okay, and followed by statement colon. Okay, this is the syntax. Remember, whenever the event in the sensitivity list occurs, the statement is executed. So when you, it is like always at the rate, whenever you have that condition in this brackets, the sensitivity list, based on that condition, once the condition is met, whatever the statement is the functionality that you write in, that will be executed. Let's see here. For a D flip-flop, very important. This you will see throughout your life. D flip-flop plays a lot of role. Okay, in the entire DFT career, we use even not just DFT, even for the physical design people, D flip-flop plays a major role because this is the only memory element that we consider it as a memory element in the design. We use it to store a bit of data. We use only D flip-flop. The stable flop type that we use is D flip-flop, and it is stable throughout the clock pulse and giving us rigorous results on the wafer level. So we use D flip flop only. In the industry, semiconductor industry uses only D flip flop. Okay. Now module flop input is clock, and there is data input. Input, that is a 4-bit data input. Output reg. Guys, look at this. This is the data input. This is a bus, but we have never mentioned to create this many registers. Okay, but here, see, you are mentioning reg. When you mention reg, okay, 4 bits, 4 flip flops are created, 4 registers are created to store this 4-bit of data. Okay, so this is syntax in writing the code. If you want to store the data after processing, okay, between input and output there will be functionality, right? So this is your input and this is your output. Something is happening here. That means this is flop, right? Definitely for flop you will write register. You are telling that to store data. Okay, you have to write this for a flop. Okay, for a flop reg is mandatory. So you have to store bit of data, then for all the 4 bits 4 data registers are created, and every processing that happens through this 4-bit data is stored here. Okay, so this part is the declaration. Next, moving on, always statement. We are telling at every passage of the clock, okay, every passage of the clock, whatever the data is inside the D, at the D, okay, should be at the Q. Okay, so Q is going to get the value what is present in the D. So D input, if you give 1 here, you will get 1 output. Okay, when you are saying 1 output is coming here, that means it is also storing value. When you say reg, it also stores that 1 value, and also it is at the Q. So if some logic is connected here, that value is already moved on to that logic, and the logic is executed. Okay, yesterday, I think in one of the session, in yesterday's session, I have shown you how the passage of the clock and negate of the clock we discussed, right? So the passage of the clock at the active passage of the clock, okay? So let's say okay, so this is your clock. Clock will always have a strict order with a strict width. Okay, as we are drawing it, it is not, it is uneven, but it will be perfect square clock pulses. Okay, so this is here to here 1 pulse, here to here 1 pulse, and here to here 1 pulse. So we have 1, 2, 3 clock pulses. Correct? Now this is your C, and let's say D. This is your D, and this is your Q. My data is something like this. Okay, it will not be like this, but I'm just drawing here. Okay, let me draw a little bit better in a proper way. Okay, now Q at the active edge of the clock, I mean the passage of the clock, you have written the condition that always at the active edge of the clock, whatever D input is there, okay, give to the output. So this entire output, so the D value will stay for, in a flip flop, the D value will stay for 1 clock pulse. So at this point, whatever the D is there, if it is low, so for entire cycle it will be low. That means here it is 0, 1, 0, 1, 0. This is the data, right? 0, 1, 0, 1, 0. This is understood by everyone?
Yes, sir.
Okay. And this is your pause edge, positive edge, pause edge. This is your negative edge. Okay. Neg edge, neg edge. Okay. Now, in the positive edge, when you mention always at the rate of passage of clock, whatever D is there, it should come in Q and it should stay for one active clock pulse. Okay. And it stayed here. Now again, in the second clock pulse, in the second active passage, the data is high, right? So it will be high throughout this pulse. Again, in the active third clock pulse, the data is, what is it?
0.
It's a 0. 0. Clear?
Yes, sir.
Okay. So this behavior, if you execute and see a waveform, it will be something like this. Okay. Okay, now? Right. This is understood?
Yes,
Any
sir.
questions? Okay. Moving on. So the explanation of passage defines a rising edge, transition from 0 to 1. This process will trigger only if the clock signal rises. Once the clock signal rises, the value of D will be copied to Q. Okay. So assign statement is not used within always block. Remember, while writing code, RTL code, assign statement is not used within always block. Within always block, you don't use assign statement. Okay. And you always use a non-blocking assignment. This is your non-blocking assignment. Okay. So we will see the difference between blocking assignment and non-blocking assignment. Let's see the other way of using blocking and non-blocking. And again, assigned variables need to be declared as register. Okay. That means this is your queue, right? You want something to be stored here. Some value in the D should be copied here. You need to mention register for this queue. Okay, the name reg does not necessarily mean that the value is a register. It could be, does not have to be. This is the biggest joke actually, but don't worry about it. You have to write in this way only. Okay, and we'll see examples. Other example of we have added sensitivity list of negate of reset now. One more thing came into picture is now the flop has a reset because this is a D flip flop with a asynchronous reset. Okay, remember this. This is very commonly used in designs. Okay, this is very commonly used in designs. So the flop that you use in real time will always have this reset. Okay. Now this is. Do you see here? Always begin if condition, else end. Okay. Now always at there is passage clock negate reset begin if reset is double equal to 0. If reset is equal to 0, you mention 0 to the queue. That means you don't care any value inside the design, inside the data input. You directly make the queue output to be 0. Okay, because you're telling to reset the flop. Okay, so if reset, this is asynchronous reset, that means it is coming from some combination logic. Okay, or from primary input. Okay, this is not synchronous to the clock. When you say asynchronous, that means reset asynchronous reset means it is not synchronized and it is not matching to the frequency of the clock or the behavior of the clock. Okay, right. And you do not have control. That is also a reason why we call it synchronous. Next, else statement is something that if your reset is not 0, then whatever the d value you have, give it to Q, and for this it will consider it as a clock. For if condition of reset, it will consider this, else it will consider the passage of the clock and d will be transferred to Q. Okay. So in this example, there are two triggering points. One is reset and other one is a clock. Clock is a passage and reset is a negate. Okay. So for longer statements, a begin end pair can be used like this. Okay. This is if statement of if reset is 0, Q is set to 0. This is an asynchronous reset and the reset does not care what happens with the clock. Okay. Next, D flip flop with a synchronous reset. That means your reset is properly synchronized. Now, if this is the time, if you understand this, I will explain how a reset is synchronized. I'm not sure you guys can process it now, or I can explain when we work in DFT. Once DFT starts, DFT actual concept start, we can also explain there how the reset is synchronized. Okay. For now, I think it will be too much. Okay. There is a process of reset synchronizing. Okay, to synchronize the reset. And do anybody has a question? What is reset? You can ask me. This is where you learn. No problem. Do you know or don't know what is reset? Tell me, based on that I'll explain, otherwise I'll move on. Should I explain?
Yeah, sir. Explain it.
Okay. This is a flop. Okay. Clock. Reset. Okay. I'm writing a short form of clock and reset. Okay. Reset. RST means reset. CLK means clock. Okay. Don't ask what is clock. Okay. This is a clock. This is reset. Okay. Now this is your SOC. Okay. This is your motherboard or board, whatever the PCB, whatever the final board, which is having all the components. Okay. You will have a hard reset, physical reset. Do you know there will be a physical reset?
Yes, sir.
Analog reset. There will be analog reset on the board. Okay. This is intended as input going as a reset here. Okay. This is to reset all the flip-flops in the entire SOC. Let's say SOC have 10 million SOCs, 10 million flip-flops. All flip-flops will be reset. Okay. You want to reset, hard reset. This is called hard reset. Okay. And this is a physical reset, will be available on every this. Okay. Now this is a port coming in and this is your digital block. Okay. This is SOC your digital block. Okay. Now this is your reset. This is a asynchronous reset. You don't have control. Okay. For controlling, Okay, even if clock is coming from port, it is not synchronous. You need to synchronize the clock. You don't know how the clock is coming. Okay, so that is the reason we always have internal PLLs. So we know what exact uh, width of the clock and the frequency of the clock. Okay, 1.2 gigahertz or whatever. You will get a proper uh, clock. Okay, free running clock. Now the reset is not stable, so we use reset synchronizers, double reset synchronizers. We call it as a synchronizers. So reset will be synchronized by using two back-to-back connected flip-flops with a D input of active high. Okay, this is going as a, this is, I mean, this is coming as a reset. This is reset. Okay, sometimes you can you can synchronize through this. Okay, and this goes as a reset to, once this is synchronized, it will go as a reset to the next flops once it is synchronized. This output is a synchronized output, synchronized reset. Okay, to the flop it will, this is a one that you take it as a reset to the next flops in the design. So this is called double synchronizer reset circuit. Okay, you have two flops, that is why it's double reset synchronizer. Similarly, we will have double clock synchronizers also. Depends how many clocks, how many synchronizers you want. So depends on if reset or clock are not stable and uh, are not toggling as per the need, and there is a change or shift in between. Okay, then we will try to add this. Okay, so because of this double synchronizer, the reset gets stabilized. Okay, we are stabilizing the reset and we are taking a proper reset from the second reset flop output. Okay, sometimes we take we avoid this also. We can avoid this and directly take this, depends on how the reset is. Okay, but anyway, this is the behavior why we choose reset as a synchronous or asynchronous. Okay, okay, so sorry to ask, forgot to ask, is it understood?
Yes, sir. So only for synchronous we use reset, or we use for asynchronous also.
In general, in all the internal circuits, we always use a synchronous reset. Okay, for DFT, we prefer using asynchronous reset. Again, that is a different case again. Okay, synchronous reset is not controllable. I mean, controllable in the sense you need to add cut point here for DFT. Again, the DFT concept is, again, we will not go there. In general, we are currently going through digital electronics, so we are in the RTL perception. Okay, in the RTL perception, we have to make sure this particular clock. Okay, so there is a clock pin for this particular clocks, right? This flops have clock. So this flop has a clock, the same coming from same clock. So you want to synchronize this reset with this particular clock, right? Because clock and reset has to be synchronized so that this is not toggling while clock is coming in. It should be 0. Okay, I mean active low. Okay, so it should not toggle the flop. Okay, So reset should be active low. That means it should not toggle when clock is driving this particular flop. That is the condition we need to meet. For that, you need to synchronize this asynchronous reset directly coming from the hard reset. Okay, you want to synchronize by giving in this particular clock and make it stable after the two clock pulses. In the third clock pulse, you will see the synchronized reset coming in. Okay.
Yes, sir.
So this is the value that will be going into all the flip flops. How many 10 million flops are there in the design? All will have this reset coming in. So this synchronizers will be in the early stage. Okay, this will be in the beginning of design. Okay, once always it is like synchronizer output is given to the next flops. Okay, so you'll understand this at larger scale, and when once the DFT starts, don't worry now. Okay, for now this much of knowledge is sufficient. Okay, once you go in depth, once your DFT starts, you will understand how the reset is used and all. Okay. Right. So once you have a synchronous reset, you don't need to worry about reset anymore. You just have to depend on the clock, active clock. You just give the sensitivity list only for the clock, but still the condition is still there. Okay. So the sensitivity is only with the clock, but still. Okay. So reset always behaves as per the clock rises. So reset only happens when the clock rises. This is called synchronous reset. Okay. So there is another thing again, D flip flop with enable and reset. This is a different case we will see in DFT. There is a pin called enable. So only if enable is high, then only D will be going into Q. Otherwise, flop will reset. Okay, for this again passage clock and negate of reset. Okay, and see that enable is not part of your sensitivity list. Okay. Moving on, this is D latch. So D latch is something always depends on D input and the clock. So even for a latch, you will have a clock. We normally call it as enable, but you will still in real time we properly give a clock. Whatever the clock you see for the flop, the same clock will come to latch as well. Okay, so the latch is the level sensitive. We have two levels, high and low. Okay, high is 1, low is 0. So in a one full cycle, you have one high, one low. So if there is a data change from half cycle, within half cycle, the data will again change in the second half cycle. Okay, it will not, data will not be stable throughout the clock pulse. That is the problem with the latch, that don't use latch to store data. Okay, only for temporary usages and clock gating cells and all. We will learn that part of DFT. So latch is also a memory element similar to flip flop, but it is level sensitive. So depends on both clock and D input. Okay, if clock is given, whatever the D value is there, it will come to Q. But sensitivity list is always having clock and D. Okay. So we use non-blocking assignments, and we do not use assign within the always block. The conditional assignment statements we don't use. We always use non-blocking assignments. So basics of always statements is see always at the rate of passage clock. Whatever value is in D will be stored in the special. Okay, and the opposite value of special is again stored in normal. This again, if see, this is simple assignment. This is output of out of. You see, this is out of your statement. This is one always with a statement. This is one set, and this is again different. This has nothing to do with this. Okay, and this has nothing to do with again this. In terms of conditional statement. Okay, so always followed by Q normal. This has to be proper non-blocking statement. This is your non-blocking assignment. Okay, you have to use like this. But here you cannot use as a statement. You can use as a statement after statement, like this. Okay. Right. You can have as many always blocks you want in the design based on the functionality you want to write. Okay. So why does an always statement memorize? Memorize is something that you are making the storage of the d value in the clock based on the active passage of the clock. Okay, so q value stored in d, it is memorizing because you're writing a register, okay, on the active edge of the clock. So q value is preserved or stored. This is useless, forget it. Next, we have seen we always use if else conditions needed. Okay, we can use it. We can also use isn commands after the always statement ends. Okay, so we can write the case statement like this, always with a case begin case with the statements and end case. We have seen three different ways, right? We have seen begin, end, if else, and a case statement. You can write whatever way you want. So non-blocking statement and blocking statement. As you can see, non-blocking is the less than or equal to symbol. Blocking is just using equal symbol. Okay, so in real time we always use non-blocking statements. Okay, so which will not block the process. So the process will always be there in a larger code when you write. Okay, so all assignment statements are made in parallel and process flow is not blocked. Whereas blocking statement, every condition a is equal to 2.b01. Okay, the value is stored. Now a is 202.b01, and now that is executed, and then next b is equal to a, that is executed. B is now 2.b01 as well. So this is like something like C++. Okay, so here everything here also see a b, the value is stored once it ends. Okay, and the statement is done, then only the value is assigned. It will wait until end. Okay, values are assigned at the end of the block. Here immediately when you say equal, that means it will directly transfer it to a. Okay, so this is not suitable and we don't use it. Okay, So this is blocking statements. This is non-blocking statements.